Good day, students. This is topic 2, lesson 3, parallel and perpendicular lines. In this lesson, we're going to look at specific theorems that are involved with parallel and perpendicular lines, and how we can use those theorems to solve specific problems. So before we do that, we have to ask ourselves a couple questions. The first one is, how can you prove that two lines are in fact parallel? Well, if we look at two angles that are given to us and we see that those angles are formed by a transversal that cuts two lines, then we can say or look for what type of relationship those angles have. If the relationship of those angles show to be congruent, then we can say they're either corresponding angles or they are alternate angles. If we see that the relationship between those two angles are supplementary, then we can say that those angles are same side. So if that's the case, either they're supplementary or congruent, then we can say by the converse that those two lines are in fact parallel. And then the second question we have to ask ourselves is, what are some key ideas about perpendicular bisectors of a segment? Well, if you know that a line is a perpendicular bisector, then you know that any point on that line is equidistant from the end point of the segment that is being bisected. And then the converse is also true. If you see that the point a point is equidistant from two endpoints of a segment that's being bisected, then you know that point has to be on the perpendicular bisector. So now let's get into some examples of how we can work with parallel and perpendicular lines. So here we have example 1, and it says in the diagram below, we have lines N and M, and they are cut by the transversals P and Q. And they're asking us what value of X would make lines N and M to be parallel. We need to state the converse theorem or postulate that was used to solve for X. So as you can see, we have X given to us, and we see X is on the transversal line of Q. So we have our transversal line of Q here. But they also give us some other values of angles. They give us angle 30 and angle 80. Well, I need to find an angle that is on this transversal line Q because we need to find some type of relationship with X. Well, as I can see, both of these angles, 30 and 80, are on the same line. So they are on this line that is created here. And we know that if we have angles on the same line, then those angles are called to be supplementary. That means that they add up to equal 180 degrees. The only problem is I'm missing an angle here that's created with this line. So in order to find this angle, we can just simply take what we know about lines. We know that if I add 30 and this angle that's unknown and 80, we know that they all equal to 180 degrees. Now we're just simply solving for X. So I would have X plus 110, which will equal 180. And if I subtract 110 from both sides, I know that's going to leave me with 70 degrees. So as you can see here, we know that this now angle we didn't know is now 70 degrees. Now that we know this angle is 70 degrees, we can look at what relationship this angle of 70 degrees has with the angle X. Well, I see that both of the angles are touching the transversal line of Q, and I see that both of the angles are on the same side of the transversal. So that only leaves two options for me, either the same side, interior or exterior, or corresponding angles. Well, I see that neither one of these angles are interior or exterior. One is inside and one is outside. So I see that the angles are on the same side of the intersected lines of N and M. So that tells me that these two angles are in fact corresponding. And we know corresponding angles are in fact congruent. So if they are corresponding angles and they're congruent, that means X would equal 70 degrees. And because we're proving that these two lines are in fact parallel, it would be the converse of corresponding angles. All right, so let's look at example 2. As you can see, example 2 is a proof, and it says write a 2-column proof of the converse of the corresponding angles theorem. So here they give us that lines M and N are cut by a transversal T. So we have, let's go ahead and highlight transversal T is here. And they tell us, or they give us the information that angle 1 and angle 2 are in fact congruent. They want us to prove that lines L and M are in fact parallel. So they give us this key here on the right. Oops. They give us a key on the right. And we can use this key to fill in the reasons that we have for our proof. And just a hint, we can use some of these reasons more than once. So if I look at the first statement, it says lines L and M are cut by a transversal, and then we also have angles 1 and 2 are congruent. Well, obviously the reason for that would be given because it is stated in our problem for the proof. Statement number 2 says that I have the measure of angle 1 is equal to the measure of angle 2. Well, if we look back to statement number 1, it tells us that the angles 1 and 2 are in fact congruent. So if I have two angles that are congruent, I know in fact that congruency does mean equality. So that means that if two things are congruent, they are also equal. And the reason would be the definition of congruence. And we see that's one of our options here. The third statement says that angles 1 and 3 are supplementary. Well, let's go ahead and look at that. Angles 1 and 3 are in fact on the same line of transversal T, and that is with the intersected line L. So we do see angles 1 and 3 to be on the same line as supplementary. So if two angles are said to be supplementary and we see that they are on the same line, well, the reason would be that they are a linear pair. And that would be the linear pair theorem. So we have another definition used. Statement 4 says that the measure of angles 1 and 3 when added together equal 180 degrees. Well, if something is supplementary and it's a linear pair and it adds up to 180 degrees, the reason tells me that this is the definition of supplementary angles. As you can see, another one of our reasons used. Statement 5 says that we have now the measure of angles 2 and 3 when added together are now 180 degrees. Well, let's think about this. If we look back at statement 2, statement 2 tells me that the measure of angle 1 is equal to the measure of angle 2. And if we jump down to statement 4, I have the measure of angle 1 plus the measure of angle 3 equals 180. Now, when we look at statement 5, we see now something has been replaced in this equation. We see that the measure of angle 2 has replaced the measure of angle 1. Well, let's think about this. Why would we be able to replace this one angle with another? Well, if in statement 2 it tells us that these two angles are in fact equal, then that means that whether I have the measure of angle 1 in this equation for statement 4 or the measure of angle 2 in the equation for statement 5, both are equal to each other. That is the definition of congruence. They're equal. So that means I can swap out or switch, or how we would say in geometry or in mathematics, we would use the substitution property of equality, meaning that if I see that two things are equal to each other, it doesn't matter which one I use because they have the same value. So once again, if I have the measure of angle 2 and 3 when added together equals 180 degrees, in statement 6 I can say that these two angles are in fact supplementary. And if they are supplementary, which was stated in statement 5, the reason is the definition of supplementary angles. So as you can see, oh, I forgot to check off substitution. And as you can see, we use the definition of supplementary angles again. And then lastly, statement 7 tells me that because I was able to prove that two angles from both lines L and M had some type of relationship, I can now state that lines L and M are parallel. But the reason being, if I look at angles 2 and 3, so let's highlight that, use a different color. If I look at angles 2 and 3, we see angles 2 and 3 are on the same side of the transversal, and they are in between the two lines L and M. So that tells me that this has to be the converse of same side interior angles, and that's mentioned here, and we can check off for a given. And that would complete our proof to show that these two lines L and M are in fact parallel, given corresponding angles. Okay, example 3 says we use the given angle relationship to decide whether the lines are parallel, and we need to explain our reasoning. So they tell us the measure of angle 4, which is here, is x plus 20, and they tell us the measure of angle 8, which is here, is 2x plus 5. And they also tell us that x is 15, so they give us the value of x. And we need to prove why these two lines are in fact parallel. So first I have to show what type of relationship these two angles have before I can prove the lines are parallel. And we can do that by using the value of x to plug back into both of the expressions that were given for the angles. So the measure of angle 4, we know is x plus 20, but to substitute x, we're going to put in 15. And I know 15 plus 20 gives me 35. So I know the measure of angle 4 is 35 degrees. And then for the measure of angle 8, they gave us the expression 2x plus 5. But instead of having the x, we're going to go ahead and replace that x with 15. So I have 2 times 15, which is 30, plus 5 is 35. So I know the measure of angle 8 is 35 degrees. So I see that both of them have the same measure for their angles. So that tells me that angle 4 and angle 8 are congruent, corresponding angles. And I know they're corresponding because both of the angles are on the same side of transversal T, so I'm highlighting transversal T. And they are on the same side of the intersected lines L and M. So they are both below lines L and M. So because we see that angles 4 and 8 have a relationship, and that relationship is that they're corresponding angles and that they're congruent, we can say yes, in fact, these two lines L and M are in fact parallel. And they are parallel because of the converse of the corresponding angles theorem. All right, so we're going to go ahead and switch gears and go to example 4 and looking at perpendicular bisectors. So in example 4, we have part A. It says prove the perpendicular bisector theorem using reflections. So here we're giving a paragraph proof, and they give us that P is on the perpendicular bisector M of segment AB. So let's go ahead and highlight the perpendicular bisector of M. So M is here. That's our perpendicular bisector. And we see point P is in fact on that perpendicular bisector. Okay. And that perpendicular bisector is bisecting segment AB. So the proof starts off saying consider the reflection across line M. So we're going to look at a reflection across line M. Then the reflection of point P across line M is also going to be point P. So think about this. If I have point P on line M and I wanted to reflect across line M and P is on the line, that means P is not going anywhere because P lies on line M, which is the line of reflection. And we can remember this back from topic 1 when we talked about reflections as transformations. Anytime you have a point on the line of reflection, that point remains exactly where it is. So also, the reflection of point A, So remember, point A is one of the endpoints on line segment AB. Across line M is B by the definition of reflection. So remember, the distance from A to the line of reflection, so this distance right here, of some distance, is going to be equal to the same distance that we have from B to the line of reflection, so whatever that distance is. So these two distances are going to be exactly the same. All right, so because we have these distances as being the same, and because we see that point P is on the line of reflection, that tells us that therefore PA, so this distance from P to A, is equal to the distance from P to B. Because if the distance from A to the line of reflection is the same as the distance from B to the line of reflection, and P is on the line of reflection, we know that these two distances are in fact the same, congruent, equal, because reflection preserves distance. And we're going to see that in part B of example 4. So now that we've proved the perpendicular bisector theorem by reflection, we're going to put it into practice. So part B says use the diagram shown, and they tell us that segment BD is the perpendicular bisector of segment AC. So let's go ahead in our diagram. I'm going to highlight the perpendicular bisector, so that's BD here, that's our perpendicular bisector, and I'm going to name it PB. So this is our PB. And they tell us, suppose ED, so from E to D, let me get a different color. From E to D, this is 16 centimeters. And then from D to A is 20 centimeters. And this is 16 centimeters. We want to find from D to C. This is the segment that we're looking for. So let's work out what we already know. We know that BD is perpendicular to AC. We know this is true. And if PD is perpendicular to AC, we know point D is on the PB, on the perpendicular bisector. So if point D is on the perpendicular bisector, then what do we know from the distance from A to D and from C to D? Well, I know from D to A and from D to C is going to be the same. These two distances are going to be the same because we just said any point on the perpendicular bisector has the same distance from the endpoints to the reflection line or the perpendicular bisector. We just said that in part A. So because DA is equal to DC, then I can conclude that DC is also going to be 20 centimeters. Okay, let's look at the next one. So the next part says, suppose EC is 15 centimeters. So from E to C is 15 centimeters. And from B to A is 25 centimeters. We want to find BC. Well, again, we already know that BD is perpendicular to AC. They gave us that in the problem. And as you can see, point B here, point B, we know is on the PB. It's on the perpendicular bisector. So once again, if B is on the perpendicular bisector, then what can we say about the distance from B to A and B to C? Well, I know that they're going to be equal because we know the distance from any point on the perpendicular bisector to the endpoints are going to be the same. So BA is equal to BC. So we know that these two segments are the same. Because I know these two segments are the same, then I can conclude that our segment BC is also going to be equal to 25 centimeters. Okay, so here we have example number 5. It says that we have segment AD is 10 inches long, so we have this is 10 inches. And segment BD is 6 inches long. So from B to D is 6 inches. And they want us to find the length of segment AC. So we're trying to find this full length here. So first, before we dive right into trying to find segment AC, let's look at what the figure actually gives us. It gives us some information. First, they identify AD, segment AD, and CD as being congruent by these tick marks. And remember, if two segments, or two of anything, two figures, are congruent, then that tells me that the measures of those figures are also equal. So if A to D is 10 inches, that tells me from C to D, it is also 10 inches. Another thing that we can note is that we have this point B, or D, and B here, okay? So let's first look at D. D from A and D from C have the same measure. So I know that if I have some point that is the same measure from an endpoint of a segment, that point has to be on the perpendicular bisector. We just learned that. So I can easily say that segment BD is our perpendicular bisector. So that would also state to be true from points B to A and B to C. So we can also conclude that from B to A would be the same distance as from B to C, because B is also on the perpendicular bisector. So now that we have all this information, we can make some statements to be true. We can first say that segment BD bisects segment AC. That's statement number one. We can say that BD is the perpendicular bisector. We can also say, since we're trying to find segment AC, we can say segment AB is congruent to, or let's since we're talking about measures, we can say segment AB, the measure of segment AB is equal to the measure of segment BC. And because that's true, since we're trying to find AC, we can also say that the full length of AC is equal to twice that of BC. So all this is important for the next step that we're going to take in trying to find AC. So because I'm trying to find AC, and because I know BC is twice, I can take 2 times of BC to get AC. I really only have to find BC and then multiply that by 2 and to get me the full length of AC. Which leaves me with this figure that I'm going to redraw from the problem. So if I'm only looking at the right side of this figure, I have, ladies and gentlemen, a right triangle, where from D to C we already know is 10 inches. And we know from B to D is 6 inches. That's given in our problem. So here now our task for right now is to find BC, and that's going to help us find the full length of AC. Now, if we look at this figure knowing that it's a right triangle, this takes us back to middle school. If I have a right triangle given 2 sides of that right triangle, and I'm needing to find a third side, then we know we have to use the Pythagorean theorem, which states that every side or every leg squared and added together equals the hypotenuse squared, which is C. So A and B are my legs, and C is my hypotenuse. So let's go ahead and label our triangle. BD, which is 6 inches, is a leg. And then B to C is a leg. And then C to D is my hypotenuse. So essentially we have the leg, one of the legs, and the hypotenuse. So if we wanted to set this up using my SSS method, we can say that we have BC squared, which is one of my legs, plus BD squared is my other leg, which is equal to CD squared, which is my hypotenuse. When I start plugging stuff in, I don't know what BC is, so I'm going to keep that as is, BC squared. I do know BD, that's 6, and that's going to be squared. And I know what CD is, that's 10 squared. And now we just solve. So we have BC squared plus 6 squared is 36, 10 squared is 100. We're going to subtract 36 from both sides, so that leaves me with BC squared equals 64. In order for me to get rid of this square, I take the inverse operation, which is to take the square root of both sides. So I'm left with BC is equal to 8, and that is inches, ladies and gentlemen. So I know now, let's go back here. I'm going to erase all this. I know now that BC is 8 inches. And that means here in our little diagram, we can replace that with 8 inches. And because BC is 8 inches, and we see it's congruent also to AB or equal to AB, we know that AB is also 8 inches. So we can come back to what we originally had where we said AC equals twice that of BC and just plug that right in. AC equals 2 times 8, so I know AC is going to be equal to 16 inches. So in fact, there's our answer, ladies and gentlemen. AC is 16 inches long. All right, so let's take a look at our last example, example 6, and it says consider the diagram below. We have 2 parts. We're going to find AB, and then we're going to find CD. So let's start with AB first. So before we start with AB, let's identify some information that we already see. We see that line segment BD here intersects line BD intersects line AC, and it creates a perpendicular line. And it tells us here, based on that information, that from B to A is the same measure, or is congruent to B to C. So that tells me that B is on the perpendicular bisector. And if B is on the perpendicular bisector, then that means that BD is our PB, perpendicular bisector. So if that's the case, then I already know my setup is going to be that the measure of AB is going to be equal to the measure of BC, because B is on the perpendicular bisector. And that's the case. If that's the case, then I can substitute AB with 7x, that's given in our diagram, and I can substitute BC with 5x plus 12. And now, ladies and gentlemen, it's just about solving. So I'm going to subtract 5x on both sides, so that leaves me with 2x equals 12. I'm going to divide 2 on both sides, so that leaves me with x equals 6. But the question did not ask me to find the value of a variable. It asked me to find the value of AB. So that means I'm going to take that x equals 6 and plug it back into what AB stands for, and that is 7x. So 7 times 6, that gives me 42. So the length of AB is 42. All right, so let's go ahead and look at part B. So here again, we saw that B was on the perpendicular bisector, right? B was on our perpendicular bisector for part A. And we also see that D is on the perpendicular bisector as well. So that tells me if D is on the perpendicular bisector, that means that from D to A has the same distance, or is congruent to, from D to C. So if that's true, then I can set up an equation to say that segment CD is equal to the length of segment AD. And that's in fact the segment that we're looking for, CD. CD from the diagram I see is 6y plus 18. And AD I see is 11y plus 3. And here, ladies and gentlemen, now we're just left to solve. I'm going to subtract 6y on both sides. So I'm left with 18 equals 5y plus 3. I'm going to subtract 3 on both sides, so I'm left with 15 equals 5y. And then I'm going to divide, so now I have y equals 3. And the question asks us to find the value of CD. So that means I'm going to plug it back in. So that means I get 6 times 3 plus 18. 6 times 3 gives me 18. And then 18 plus 18 gives me 36. So therefore, ladies and gentlemen, we are here with CD as 36. Now we can always go back and check to make sure that these values are in fact correct. AB is supposed to be equal to the length of BC, so that means I can take the value of X, which is 6, and plug it into BC to make sure I'm correct. So 5 times 6 plus 12, 5 times 6 is 30, 30 plus 12 is 42, so I know for sure I'm correct here. And then again, we know that CD is equal to the length of AD, so I can come over here and check 11 times Y, which is 3, plus 3. 11 times 3 is 33, plus 3 is 36. So I know for sure I'm correct there. All right, students, that concludes our lesson for today. Please make sure that you're going back over your vocabulary and your warm-up activity in your OneNote class folder. And I will see you in class, guys. Have a great day.